What if a computer could answer both yes and no at the same time? What if a single particle could exist in countless places simultaneously? This is not fantasy. This is the reality of quantum mechanics. Quantum computers harness this strange property to perform calculations that would be impossible for conventional computers. In 2019, Google claimed quantum supremacy. They executed a specific experimental task in about 200 seconds, something estimated to take an extraordinarily long time on classical machines of that era, though this estimate could change with algorithmic improvements. In fact, IBM countered that it was theoretically possible in about 2.5 days, and the debate continues today. But here's where a crucial question emerges. Why are quantum computers so fast at certain problems? And will this technology truly change the world? Today, let's explore the astonishing principles behind quantum computing and the future it may unlock. By the time you finish this video, you'll understand how the very nature of computation might fundamentally transform. Chapter 1. Overlapping Possibilities. First, let's start with how classical computers work. The computers we use process information in bits, zeros, and ones. A switch is either on or off, that's all. Simple, clear, predictable. But quantum bits, qubits, are different. A qubit can hold both 0 and 1 simultaneously. This is called superposition. Picture a coin spinning in midair. It's both heads and tails. Following his 1981 lecture, Feynman published the paper Simulating Physics with Computers in 1982. He argued that nature is quantum mechanical, so to simulate nature we need quantum computers. And here's where a crucial question emerges. If one qubit can hold two states simultaneously, how many states can two qubits hold? The answer is 4. 3 qubits, 8 states, 4 qubits, 16. In other words, the state space represented by n qubits grows exponentially as 2 to the power of n. However, this doesn't directly translate to exponential speedup in computation. Speed advantage depends on the algorithm and error rates. It's problem-specific. Superposition gives us the ability to explore possibilities simultaneously. But the true power of quantum computers lies in another strange phenomenon. So let's see what this phenomenon makes possible. Chapter 2. A Bond Beyond Distance. Superposition alone doesn't reveal the full picture of quantum computing. The other key is quantum entanglement. This is the phenomenon Einstein called spooky action at a distance. Two particles, no matter how far apart, have states that correlate instantaneously, though this doesn't enable faster-than-light communication. Yet their correlation defies distance. In 1964, Bell presented Bell's inequality in his paper on the Einstein-Podolsky-Rosen paradox. He predicted that if quantum mechanics were correct, correlations unexplainable by classical physics should be observed. And experiments proved quantum mechanics right. Particles truly are entangled across distance. The 2022 Nobel Prize in Physics was awarded for pioneering experiments in quantum information science using entanglement, including those demonstrating violations of Bell's inequality. Quantum computers use this entanglement to correlate qubits with one another. Entangled qubits influence each other, and by combining superposition with interference, we can design computational processes that favor specific answers. This is not a metaphor. This is physics. Using quantum gates, we manipulate qubit states to execute complex calculations. But here's a major challenge. Quantum states are extremely fragile. The slightest environmental disturbance causes decoherence, and information is lost. To make quantum computers practical, error correction technology, creating stable logical qubits from many physical qubits, is the key. Let's think about what this means. If we can achieve reliable logical qubits through error correction, significant changes could occur in specific fields like cryptography, drug design, and optimization problems. A quantum computer isn't just a faster computer. It's an entirely new kind of machine. So what does this technology actually make possible? And what does the path to practical implementation look like? Let's explore. Chapter 3. A Door to the Future. The applications of quantum computing are remarkably broad. First, cryptography. Current internet security relies on the difficulty of prime factorization and discrete logarithm problems, like RSA encryption and elliptic curve cryptography. In 1994, Peter Shor discovered a quantum algorithm that makes prime factorization efficient. In the future, if large-scale quantum computers with error correction are realized, they could theoretically break current public key cryptography efficiently. In fact, in August 2024, the U.S. government's NIST officially announced the first quantum-resistant cryptographic standards, MLChem, MLDSA, and SLHDSA, and the world has begun transitioning. This isn't a future problem. It's happening now. Next, drug design. Developing drugs requires accurately simulating molecular interactions. Quantum chemistry simulation is one of the most promising candidates, but practical precision and advantage at scale are still being researched. Error correction and methodological improvements are key. Then there are optimization problems. In logistics, finance, and energy sectors, we need to find optimal solutions from countless options. Applications to optimization are promising, but it hasn't been confirmed that quantum is always faster than classical. Currently, verification and demonstration are ongoing. Think about this for a moment. If quantum computers become practical in specific fields, our society could change profoundly. Cryptography, medicine, logistics, all could be restructured by quantum power. Yet between 2023 and 2024, Google and Microsoft achieved historic breakthroughs in demonstrating logical qubits that compute while correcting errors. Error correction and achieving reliable logical qubits remain the greatest barrier, but light is beginning to break through. Quantum computers have opened a door to the future. And beyond that door lie problems to solve. Alongside hope, that's beginning to materialize. So let's organize what has emerged from this exploration. Chapter 4. The World Revealed. Today, we've deeply explored the astonishing principles of quantum computing and the future it may unlock. Superposition, quantum entanglement, quantum gates. These strange properties hold the potential to transform the nature of computation itself. Let me summarize what has been revealed from today's exploration. First, qubits hold 0 and 1 simultaneously, expanding state space exponentially. However, speed advantage depends on algorithms and error rates. It's problem-specific. This strange property of superposition gives us the ability to explore possibilities simultaneously. Second, quantum entanglement creates correlations beyond distance, and by combining superposition with interference, we can design processes that favor specific answers. This phenomenon, which Einstein called spooky, is at the heart of quantum computation. Third, quantum computers show promise in cryptography, medicine, and optimization, but achieving reliable logical qubits is the key. Breakthroughs in error correction are beginning to open pathways toward practical implementation. These insights reveal the potential for the very nature of computation to fundamentally transform. A quantum computer isn't just a faster machine. It holds the potential to provide entirely new kinds of solutions for specific problem settings. The quantum world completely defies our intuition. Yet within that strangeness lies the power to transform the future. I feel a sense of awe at what this technology might bring to humanity. Quantum computing is still in its infancy, but its potential is immeasurable. So I ask you, if error-corrected quantum computers become fully practical, how will society change? And in which fields, and in what ways, should we use the power of quantum? These questions don't yet have answers, but continuing to ask them moves us forward. The quantum door has been opened. Let's explore together what lies beyond. After finishing this video, when you return to everyday life, I want you to consider something for just a moment. The computer you're using can only handle zeros and ones. But in the quantum world, 0 and 1 exist simultaneously, become entangled, and interfere. Keep this difference in mind. Your understanding of what computation is might shift, even just a little. And your imagination of the future might expand, even just a little. Share your insights in the comments. Your questions are what drive this channel forward. Thank you for joining me on this intellectual journey today. At Mindshift, we explore cutting-edge science, like quantum computing, and its philosophical implications. If you're interested in themes like the cosmos, consciousness, and technology, please subscribe and turn on notifications. Let's transform how we see the world together. Until next time.